Step 2 in this process is pyruvate oxidation and the citric acid cycle. So following glycolysis, we still have a lot of potential energy remaining in what was our glucose molecule, this 6-carbon sugar. So let's think about where some of that potential energy might be. Well, we know that when we split the glucose, which had 6 carbons, we created 2 molecules of pyruvate that each have 3 carbons, and we created 2 molecules of NADH. Now this is in addition to the net gain of 2 ATPs that we had. And remember, because of the second law of thermodynamics, where did some of this other energy go? It was lost in the form of heat. That's exactly right. Now, if there's oxygen present, pyruvates are going to enter the mitochondria. And so remember, these pyruvates are 3 carbons that we created from glycolysis out in the cytoplasm. If oxygen is present, pyruvate oxidation will occur. Now here's what happens during pyruvate oxidation. For each pyruvate, when the pyruvate passes from the cytoplasm through these helper proteins in our mitochondrial membrane, a carbon is going to be pulled off to form carbon dioxide. And using a coenzyme A, each pyruvate is going to be converted into a molecule of acetyl coenzyme A. Now these acetyl coenzyme A molecules each have 2 carbons. So here comes our 3-carbon pyruvate. A carbon is pulled off to form carbon dioxide, and what remains after coenzyme A acts on this is an acetyl coenzyme A that has 2 carbons. In addition, this oxidation creates electrons which are going to reduce NAD to form another energy carrier or electron carrier in the form of NADH. Now, think about this for a moment. How many pyruvates are created from a single molecule of glucose? Well, that would be 2, correct? So, after glycolysis of a single molecule of glucose, pyruvate oxidation can occur twice because we would begin with 2 molecules of pyruvate. Now, following pyruvate oxidation, our acetyl coenzyme A's can enter what is called the citric acid cycle in the matrix of our mitochondria. Now, this is also known as the Krebs cycle, for it was discovered by Hans Krebs in the 1930s. Now, your book goes through a lot of these intermediates, and I want you to learn this in simple form. So, here's the way that the Krebs cycle works. For each acetyl coenzyme A that enters the citric acid cycle, the citric acid cycle is going to spin like a wheel. And as this wheel spins, we're going to produce 2 molecules of CO2, which means that now the catabolism of glucose is complete. Each time the wheel spins, we're going to produce 3 NADHs as we reduce the NADs. And then we're also going to take and produce another electron carrier called FADH2. And so we can see here another pair of electrons is going to reduce FAD to make FADH2. In addition, each time the citric acid cycle spins, we create 1 ATP. So if we look at this process as a whole, step 2, pyruvate oxidation and the Krebs cycle works like this. We've created 2 pyruvates through glycolysis. Each pyruvate enters the mitochondria by being oxidized, and as each pyruvate is oxidized, we lose CO2 and we form an acetyl coenzyme A. So from 1 molecule of glucose, we create 2 molecules of acetyl coenzyme A and 2 CO2s. Each one of these acetyl coenzyme A's can spin the citric acid cycle wheel, and each time the citric acid cycle wheel spins, we produce 1, 2, 3 NADHs, 1 FADH2, and a single ATP. Now, let's kind of review what's happened up until this point. Again, this is a good slide for you to refer back to, right? So here we have glycolysis out in the cytoplasm. We take one molecule of glucose, we end up with a net gain of 2 ATPs, 2 NADHs, and 2 of our 3-carbon pyruvates. Each pyruvate can be converted into acetyl coenzyme A, which produces a carbon dioxide and an NADH, and each acetyl coenzyme A spins the citric acid cycle wheel to produce 3 NADHs, 1 FADH2, and 1 ATP, and 2 more carbon dioxides. By this time, the 6 carbons from our single glucose molecule have been completely converted into 6 molecules of carbon dioxide, which means that glucose is now completely catabolized. And so far, we've made 4 ATPs. So where is all of this energy? 4 ATPs per glucose is not a very efficient process. Well, if you think about it, most of this energy is going to be tied up in these electron carriers. So far, we've created 10 molecules of NADH and 2 molecules of FADH2. And it's these energy carrier, these electron carrier molecules that are going to be routed to the cristae of the mitochondria for the final third step.